Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered if seeing is truly believing, especially when things change size right before your eyes? This new study dives deep into how well our brains can recognize faces even when they appear at different sizes our eyes perceive. You know, we walk around and objects stay the same real size, but how big they look on our eyeballs changes all the time because we move closer or further away. For years, scientists thought our brains were amazing at handling this, saying we have size invariance. This means our perception of an object shouldn't really change even if its image on our retina gets bigger or smaller. But here is the catch. Most of the time, scientists tested this by changing the size of the image on a screen while you sat the exact same distance away. That is not quite how we see things in real life. In real life, a face doesn't suddenly become a tiny doll or a giant billboard. Its actual physical size stays the same, but its size on our retina changes with distance. So these researchers decided to test face recognition in a more real-world way. They wanted to see if our ability to tell one face apart from another, a task scientists call face discrimination, is affected when the size of the face on our retina changes. They even used two ways to change the retinal size. One way was like in the lab, changing the actual size of the face image on the screen while keeping the viewing distance fixed. The other way was more naturalistic, keeping the face's real-world size the same, but changing how far away it was, which naturally makes its image on our retina smaller. To assess face discrimination performance, we employed a well-established morph paradigm. Original solution. So how did they do it? They used a clever trick called a face morph. Imagine you have two different faces. They blend them together, creating a spectrum of faces that gradually change from one identity to the other. It is like a visual slider. Participants were shown pairs of these morphed faces and had to say if they saw the same face or two different faces. This helps measure how precisely people can detect subtle differences. To estimate the sensitivity to retinal size changes, we adopted the ideal observer framework. Original solution, they also used something called an ideal observer framework. Think of this as a perfect theoretical guesser. It is like a benchmark. If humans are perfectly size invariant, their performance wouldn't deviate much from this ideal in different size conditions. By comparing how human performance changed compared to this ideal observer, they could see how imperfect our size invariance really is. We tested face discrimination sensitivity to retinal image size in 5 experimental conditions, manipulating both retinal image size and viewing distance. Original solution, they set up 5 different experimental conditions. Some involved changing the face image size while you stayed close. Others involved keeping the face image the same size but moving you further back, or keeping you further back but making the face image larger. It was a really well-thought-out design to tease apart the effects of retinal size and viewing distance. We found that the difference detection threshold dt was not influenced by retinal size changes or viewing distances we manipulated from this original solution. So what did they find? The first key finding was that the basic ability to tell when two faces are different, what they call the difference detection threshold, or DT, didn't really change much. Whether the face was big or small on their retina, or whether they were close or far, people could still detect the point where faces started to look different at about the same level of morph. That sounds like good news for size invariance, right? However. Face discrimination was significantly worse for smaller retinal image sizes, the original image solution. But here is where it gets interesting. While the threshold for detecting a difference stayed the same, their overall performance, how accurately they discriminated faces, that is where the real story unfolds. They found that when the retinal image size of the faces was smaller, face discrimination performance got significantly worse. This happened whether the size change was naturalistic or lab-like. Worse face discrimination performance at smaller retinal image sizes were significantly associated between naturalistic and lab-like conditions. Original solution even more compelling. This worse performance with smaller images was consistent across both the naturalistic and the lab-like conditions. This suggests that simply having less information on the retina due to smaller size, regardless of the why behind it, impacts our ability to tell faces apart. Results indicate that face discrimination shows imperfect invariance to retinal size, and importantly, this appears independent of viewing distance, original solution. So the big takeaway, face discrimination is not perfectly size invariant. Our ability to distinguish between faces is indeed sensitive to how large the face appears on our retina. And importantly, this sensitivity seems to be about the information reaching our eyes, not just about how far away we are. Even when they tried to control for viewing distance, smaller retinal images led to poorer performance. Scroll deviation from ideal observer calculation. Original solution, remember that ideal observer we talked about. The researchers found that with smaller retinal images, people's performance deviated more from this ideal perfect observer. It is like their ability to finely tune into face details got fuzzier. They looked at this using measures like error rate and deviation from ideal observer, and J&D, which is a measure of how precise their perception was. All these showed the same pattern. Smaller retinal images meant worse performance, meaning more errors and less precision. Scroll investigating retinal size. Related discrimination benefit at 40% morph. Original solution. They even did a specific test at a level where faces were already somewhat different, about 40% morphed. They found that when the faces were presented at the largest retinal size, people were significantly better at spotting those differences compared to when the faces were presented at the smallest retinal sizes. This directly shows that having a bigger image on your retina really helps you pinpoint those fine facial details. Scroll individual consistency across experimental manipulations. Original solution. What is also cool is that they found some consistency in how individuals performed. If someone struggled more with smaller images in one setup, they tended to struggle more in other setups too. This suggests that individual differences in how our visual system processes size information play a role. Scroll discussion. Original solution. So, why might this be happening? The researchers suggest a few possibilities. One is that face perception might rely on specific spatial frequencies in the image. When the image size changes, the spatial frequencies present also change. And this could mess with those specialized face processing mechanisms. Another idea is that face perception is part of a larger system for recognizing people, which might involve other cues like body language or expressions. Maybe the size changes affect how well we integrate all these cues. And of course, they note that familiarity plays a big role. We're likely much better at recognizing familiar faces across different sizes than unfamiliar ones. Scroll limitations, original solution now. Like all good science, they acknowledge their study's limits. They point out that just like in real life, viewing distances can be much further than what they tested. And faces in real life at those distances occupy much larger areas on our retina than their stimuli. They also mentioned that their participants and stimuli were mostly of a similar background, and they only used young men's faces. So, their findings might not apply to recognizing faces of different genders, ages, or ethnicities, or across different cultures. Central investigation into size invariance in human face discrimination emphasizes that retinal information evident via retinal size and also retinal information resolution is critical in determining the sensitivity to facial changes. Central, what this study really hammers home is that our visual system isn't perfectly immune to changes in the size of an object's image on our retina, especially when it comes to something as complex as faces. The more information you can get onto your retina, the better you seem to be at those fine discriminations. This has implications for everything from how we design video calls to understanding why sometimes, even with the best intentions, we might struggle to recognize someone from a distance or on a small screen. Conclusion: ultimately, this research kindly reminds us that while our brains are incredibly good at interpreting the world, they still rely on the raw data our eyes send them. And when that data is smaller or less detailed on our retina, our performance can take a hit. It is a fascinating peek into the subtle ways our perception works and its limitations. Conclusion: so what are your thoughts on this? Have you ever found yourself struggling to recognize someone you know from afar? Let me know in the comments below. And if you found this breakdown helpful, give us a thumbs up and subscribe to RUBIN'S Mind Lab for more fascinating dives into the world of psychology and neuroscience. We'll see you next time.